So uncertain data, we're just going to touch on this subject and see what this looks like in terms of the concept and operational in terms of a code like OpenBugs. So there's many different kinds of ways we can run into uncertain data. Sometimes just the data itself is a little uncertain or fuzzy. We go out and we say things like, the components failed, or we see the transient, but real life, sometimes it's hard to make those judgments on, is it really failed? Is it failed in terms of what a PRA would say, or in terms of what the regulations say? And so you end up with kind of engineering discussions many times when you're doing data analysis. But in general, though, we'll run into these kinds of situations listed here on 84. So where we have censored data, so what are called interval valued observations. In other words, this will occur a lot of times when, say, you get an event that's complicated and you're not really sure when it started or ended. A good example of that is fire suppression times. You get the report that says the fire appeared to start at 8:05 in the morning, and we think the fire brigade put it out at 9:16. That's a duration, but there's uncertainty in terms of, okay, did the fire really start at that starting time you stated in the event report? And, was it really out at the time the fire brigade said it was out? Was it actually out earlier than that and they just waited some, to go into the room? Or so you get all kinds of complexities like that. The case where the failure may not be a failure or not. Sometimes you get operational failures. Sometimes you get licensing or regulatory kinds of failures where the component may be degraded, but maybe it could still work. But from a regulatory standpoint, it's declared failed. How do you treat that? Collecting data is difficult. So a lot of time we don't know exactly how many demands. If you go out and test a component, it works fine. You may not record the success. We're really good at typically recording the failures, but every time you start that pump and it doesn't do anything in terms of a failure, then maybe you record that, maybe you don't. So questions there. Again, we're not going to go through all of these examples, and depending on what kind of uncertainties you have, we'll have specific nuances of how you treat those. But there's a whole case of uncertain data in section 10 in the textbook. We'll walk through an example though, just to give you a sense of how this works. So in fact, I'll use the fire suppression time, and this is similar, I think, to Chad's issue in a sense. Almost, not exactly, because you will see this is exponential data. It's uncertain in the case of I don't know exactly at times. These have all, though, been said, okay, I have seen the outcome. The fire has been suppressed. Now, in Chad's case, the only difference would be in some of the events, it would be, the data would not say, okay, maybe the cask has been in a facility for 10 years. And so the data point, it would not say 10 years. The data point would say it's been at least 10 years. So the failure data is greater than 10 years. It could be 10 years, it could be 1,000,000 years, but the uncertainty there would say greater than 10 years. In this situation, though, I'm talking about fire suppressions events. So the first event I had, the event was recorded that the fire was put out in less than 5 minutes. I don't know, it could have been right at 5 minutes, it could have been 4 minutes, could have been 3 minutes, 50 seconds, based on the event that was recorded. I just don't know. And so I can't say precisely it was 5 minutes. It could have been 4 minutes, maybe. Same thing with event number 2. Event number 3, 15 minutes. Event number 4 was, yes, from start to finish, we put this fire out. It was exactly, and I'm making up numbers here, but exactly 14 minutes. The next one was exactly 15 minutes. 6th one, exactly 15 minutes. Now, event 7 is a little interesting. We had a fire. It may have been put out in 10 minutes, but maybe there's some things going on there. And then maybe we didn't enter the room until 30 minutes, and then we definitely saw that, hey, yeah, that fire was put out. And so there's an interval there for what we would normally put in as just a single time. So normally we would have, just or some definitive number like the numbers above that. But so we can have different kinds. We can say less than a certain time, or between a lower and upper bound, and again, in the case of like Chad's data he was talking about in the chat, it could be greater than some known quantity of time. And then time 8 then is similar in 15 minutes, 9 is 150 minutes, and then 10, the event number 10 was again between 100 and 300 minutes. So kind of a complicated data set. How would you treat this? Well, let's talk about it. We've already mentioned things like, okay, the times could be exponentially distributed. So we would have a model that's an assumption. I could relax that assumption. I could say the model is a Weibull or some other model, but in this case, let's just start with a simple model, say they're exponential. I want to figure out then a suppression rate. So I don't want a rate for each fire. What I want is an overall, what's the average rate of fire suppression at my facility? And the complication here then is the data that goes into the calculation is of a censored type. It could be censored in terms of upper and lower, or just lower or just upper. And fortunately, then most Bayesian inference tools have this concept of censored data built into them, because this is a very common situation to run into. And specifically in open bugs, one of the ways to treat this is there's an actual keyword built in called capital C, very simple keyword, but C meaning censored. And how this works is, if you remember, when we were specifying the times, we said, okay, that's going to go into this exponential distribution. We didn't put anything else on that line, because at that point when we were talking about it, we were assuming all of the times were known. We were assuming there's no uncertainty in those data points. If you have uncertainty, simply put in this C construct for censored data. Now, if you do that, then you have to specify, okay, do you know a lower bound or an upper bound? What's the censoring that's going on here? Okay. In the case where you know exactly the data point, then the lower, the upper is just that data point. So there's no uncertainty really for that. There's also a second keyword that we need to know called NA, which is a beautifully named keyword for not applicable or really not known. And so in some cases, if you don't know the value, there's a keyword called NA to help you say, I don't know that value. And then I'm not going to go into math, but essentially, when you start using censoring and NA, open bugs and other Bayesian tools, they use what's called an imputing approach. And essentially, it becomes a simulation within a simulation. So in other words, what happens here is, at the point where open bugs runs into the question, what do I do with this data point? It can either do one of three things, I think. It could either stop and say, I don't know what to do. It could just say, assume a data point based on maybe like a maximum likelihood estimate or some kind of mathematical thing. But instead of doing those first two things, what it does is says, I'm going to take all of the information I know up to this point, run sort of a simulation within a simulation to say, what could this data point actually be given what I know? And then use that data point, that new simulated data point for the iteration it's on. And then, of course, from that point, it has to do other simulations to get the Bayesian updating, but it's a simulation within a simulation. And again, that's called imputing. Okay, so it's a very powerful concept. And it's very easy to implement, as you see here. Specify what you know. Don't specify things you don't know. straightforward. So how that would look in the case of our exponential example here, again, we have to have a loop because we have multiple data points here. The time for suppression, or t.sup, is an array. I have n number of those. And so the model part of this doesn't really get that much more complicated. The only new addition really is this C for the censored, where I now say, okay, there's a lower upper bound I'm going to specify on each of these data times. The prior distribution, this is still a Jeffreys non-informative, so that doesn't really change. The data section does get more complicated, as you can see here. So instead of having one line of data like we had before, now we have to specify kind of what is known in the first line, so t.sup, and then we also have to duplicate, okay, the upper and lower for all 10 of those data points. So let's look at this a little closer. So for example, the first time, let me go back to my data. The first event was less than 5 minutes. So how I specify that is then, I don't know the time exactly. So my time sup is NA. I don't know it, but I do know that it was less than 5 minutes. What that means is my lower bound is 0. It can't be a negative time. My upper bound was fixed at 5. Okay, that point is done. So I go back. The next one, the same thing. Third one will be 15. Fourth point will be 14. So let's look at the fourth point. So the first three are NAs, all zeros, 5, 5, 15. That looks fine. The fourth data point, though, was said it's exactly 14. And to do that, you simply put in 14 for the recorded time, 14 for the lower bound, 14 for the upper bound. Very straightforward. And you do that for each data point, clear up to the last one where we had, of course, that was between 100 and 300. So we'd put in NA, 100, and 300. You run the analysis. Oops. What comes out of that, of course, is a distribution. In this case, it's a fire suppression rate that we call lambda. If I invert that, that will give me the mean time to suppress the fire. I could have done that calculation in the script. I didn't here, but it's a distribution. And you see it, even though we have a bunch of uncertain data, if you actually look at the distribution, it looks reasonable. Yeah, there's a factor of 2 or 3 in the uncertainty, but that's typical. It's not like we have some uncertain data, all of a sudden, we have these factors of 1,000 or 10,000 or, wild things going on. But the cool thing is, this red curve, the distribution, incorporates the uncertainty that you have in your data. What do I know? So I don't have to go back and just assume, oh, this was 5 minutes, this was 15, this was 20, this was 200. I don't have to make those assumptions because I could build in the times directly. Okay. Very powerful concept. Again, 2 new things here, the censored construct, and then the NA for when I have data that or when I don't have data that I normally would have had otherwise. Okay. Let's talk about the case where, that was related to times. What about if I don't really know the failures? And so maybe there's some fuzziness in my event reporting, and this event report looks like a failure, I'm not really sure. And the next one kind of looks like a failure, but I'm not really sure, and so on. So again, there's many ways why we run into these situations. And there's different ways to actually treat uncertainty in the failure count. I could make assumptions and calculate a posterior for, assume these 4 events that I'm uncertain about. Assume maybe only 1 of the 4 is a failure, 2 out of the 4, 3 out of the 4, 4 out of the 4, and then weight those. So I could kind of make this assumption and blend them all together. Or I can do the same kind of thing almost from a likelihood standpoint. And these, again, are described in the book. But let me talk about the posterior averaging approach real quickly. It's pretty straightforward. And so in the example here on page 90, I have plugging of service water, and I have 7 events that's going to describe that. And those 7 events give me all of the failures, but there's a couple of them that I'm not really sure. So there's 3 of them that if I read the event, and I go through the details of what really happened, what did the engineer say, maybe it was started working, then stopped and started working, and so on. So you go through all the details. And you get to a point where you're not really sure. It could have been 7 failures, could have been 6, could have been 5, could have been 4, because there's some questions related to 3 of the events. You're not really sure. Now, in this case, we're going to assume that for all the strainers, there was a total of 48,180 hours of operation. But I'm just not sure of how many failures. I know I have 7 records. I'm not exactly sure how many failures I had, how many pluggings I had of the surface water here. So one thing I could do, and this again is a very powerful concept, is I can go look and see, and I can actually weight these. I can say, looking at these 7 records, it doesn't really look like there was really 7 failures. More likely, the 3 in question were not failures, but I can maybe still include those. And so I can then put a different weight on these outcomes. And so I just made this up, but I could say, well, I believe most likely it's that I really only saw 4 failures. Now there's a chance that one of the records could have been a failure. There's a chance that 2 of them, chance that the other 3, could have been, and so on. And I would then just put these weights into the program, into the Bayesian inference to say, do the calculation with x equal 4 and weight that with 75%. Do the Bayesian updating with x equal 5, weight that at 15%. Do it with x equals 6, weight that at 0.075, and the last one, of course, is x equals 7 with a 0.025. Those weights have to add up to 1, and what happens is OpenBugs will run these 4 calculations kind of all at the same time and weight them all at the same time and give you one aggregated distribution that incorporate these 4 outcomes with these 4 weights. To do that, again, it's a pretty simple concept. Most of this is something we've already seen, and the only thing that's really new here is the keyword called DCAT. That stands for a categorical distribution. What a categorical distribution does is allows us to combine things based on the weighted average specified by the vector inside the keyword. And so my weights are in this vector called P. And you can see then the vector is the weights I have here. So P1 is 0.75 and so on. And this categorical distribution then takes my 4 distributions, combines them via this user-defined variable called R. And so what I'm doing is, since I have 4 versions of lambda, I will be able to mix and match those because there's a relationship between each of the 4 lambdas and the weights through this categorical distribution. And the R is what really ties those together. And so if I look at this lambda.average or AVG, that will be all 4 distributions for lambda combined with these weights. And the 4 distributions are x equal 1, x1, which is 4, x2, which is 5, x3, which is 6, and x4, which is 7. So in other words, I will have, and they all have the same time, but I will do a calculation where x equals 4, weight that by 75%. X equals 5, weight that by 15%, and so on. Combine those into this lambda.avg. They all have a Jeffreys non-informative prior. They're all using a Poisson aleatory model. we're counting the number of failures. The only thing really different here is that I just have 4 versions of reality that I want to account for. 4 possibilities. When I run the calculation, I see the output on page 93. So lambda.average. So on average, I would say that the failure rate for my service water strainer plugging is 4.0 times 10 to the minus 4. And I don't know if I put units on that, per hour. So 1 times 10 to the minus 4 per hour is my rate. And it, again, it includes the uncertainty in my event reporting. The distribution looks like this. Now, in reality, there's 4 little distributions all mixed up here. And so you really can't see that, but you know, in some cases, you actually see, you might see multi-modes. You know, for example, if you go back and change these to 25%, so 25, 25, 25, 25, and then rerun, you might actually see some different modes representing the 4 different distributions. But obviously, what's driving this result is going to be the thing with the most weight. So x equal 4 is going to be the predominant driver, if you will, of that red curve. And then second most prominent will be the thing that's weighted at 15% and so on. Okay. So again, a way to account for differences in the failure count. Okay. Let's move on to a new topic. Let's do a calculation where we want to see, we're going to calculate a failure rate, but we want to see if that has changed from either a desired level or maybe a historical average. And so, for example, maybe I'm going to buy a new component, swap it out, and I have historical data for the old component. And then I run the new component for a while, and I want to ask, you know, did the old component or the new component, is it better? So I can just compare 2 failure rates. And again, that's just a calculation we can do in OpenBugs since it's a scripting language. So in this case, we're going to ask, you know, does the new component have a higher failure rate than the old component? To do that, we have to know what the old rate was, and then we have to have information related to the new rate. So when we had the old component in, we have to have 3 things to calculate the rate. We have to have a prior, data related to that, and a model to do the Bayesian updating. So this is a failure rate, so we will assume the Poisson model is applicable. We'll just use a Jeffreys non-informative prior. And for the old component, we had, let's see. Oh, sorry. Let me back up a second. So we've done an analysis for the old component, and we determined, maybe it was conjugate, but we determined that the old component had a failure rate of 1.5, 300,000 hours in terms of gamma distribution. Now we inserted the new component, the new distribution, we're calling it lambda high, and we will assume it's a Poisson. We'll start with a Jeffreys prior. And for the new component, we've seen 2 failures in 41,861 hours of operation. When we run the script, and let me actually just jump to that to see how this is going to work out. We have really 2 things going on in this script. We have all of the infrastructure for the new component. So x.new, that is where we saw 2 failures. It is a Poisson, mu, we call that mean.new, it's lambda times t. The time was the 41,861 hours. We had a Jeffreys non-informative prior for the new on lambda. And so the blue, what's in the blue text here, we'll do the Bayesian updating calculation for the new component. We call that lambda.new in this script. The old one was lambda.old. Now, if we had data related to the old one, I could actually do the Bayesian calculation here, but in this example, we simplified it a little bit, and we just said, okay, the old failure rate was a gamma with first parameter 1.5, second parameter 300,000. And then we go back and use that step function. We ask, is the new failure rate bigger than the old failure rate? Again, if this calculation turns out to be positive, the step function gives me a 1, otherwise it gives me a 0. And this step function is calculated at each iteration, each time I do a sample. So in other words, when I go in and tell OpenBugs I want to run 1,000,000 samples, I will get 1,000,000 either zeros or ones out of this step function. Test then will tell me what is the probability, because it essentially gives me the ratio of the zeros. It gives me the ratio of the ones to the total number of samples. So if I were running 1,000,000 samples and 500,000 times the new is larger than the old, I would then get a probability out of this of 0.5, 500,000 divided by 1,000,000. I run this calculation, and when you do that, you'll see that 99% of the time, the new, or what's called lambda high on this slide, is larger than the old component. Now, again, this is a made-up example, but nonetheless, you probably would not be too happy if you put a new component in, you find out, well, there's a 99% chance the failure rate is higher on the new component than it is on the old component. And so this is that's a very significant, statistically significant value that says, yeah, you're pretty sure that the rate has changed. And of course, if you want to know what the rate is, you can calculate what's the mean failure rate of the new, the mean failure rate of the old. So you could actually see a delta there and calculate that. We did not do that in this script, but you would just want to probably add a new line to say delta is equal to, lambda new minus lambda old or something like that. Okay, but again, given what we saw on this page, old versus new, yeah, we're in a worse situation in terms of the failure rate. And I can use that same concept to ask, am I meeting a reliability goal? So instead of comparing a failure rate against some old component, I could say, take my failure rate, compare that against a reliability goal, and I can tell myself, am I meeting that goal? Let's see how that works. So we show a picture of that here on slide 99. And this is, again, a hypothetical example, but let's say I'm going to take out my diesel generator. I don't want to burn diesel fuel anymore. I want to replace that by a hydrogen fuel cell. But I want to make sure that the fuel cell is reliable. And let's assume I had a reliability goal that I want the diesel or whatever system I'm going to replace it with to have a reliability of 99% with a probability of 95%. So another ways to say that is the failure probability, again, reliability and failure probability are 1 minus each other. So if I know the reliability, take 1 minus that then tell me the failure probability should be less than 0.01 with a high probability, with a 95% probability. A little complicated because we're talking about two different probabilities, but the plot here then shows really what I want is my failure probability to be 0.01 or less. Now, I would like it, of course, to be 100% less, but I'm willing to allow a 5% chance of being above this threshold. And so that's a good way. It's a very powerful way to actually state a reliability goal. So rather than saying I want to be 100%, or 0% chance of not meeting my goal, you have to be a little realistic. And this is a way to state that probabilistically. I'm allowing a 5% chance of not meeting my goal. Now, if that 5% chance is too high, I can move this curve. I could say I want a 1% chance of not meeting my goal, or a 0.1. You know, I can move this curve however I want to specify my goal. And then, so that's one part of it. Where do I want to specify my goal? I'm saying 5% is good enough. And then I have to move this to what I want my failure probability to be. So 5% chance of being above 0.01. Or another way to say that is a 95% chance of being below 0.01. Or another way to say it is a 95% chance that my reliability is 0.99. That's a goal. I don't know if I'm meeting my goal. I have to run the Bayesian analysis because I have to calculate this red curve using Bayesian inference. So we go out, we buy the fuel cell, we test that. And guess what? We find a failure in 250 demands. We go right back to the Bayesian script. We know how to do this. We can specify a prior, a model, and we have data. And we can calculate using the step function in OpenBugs, are we meeting that goal or not? And so what that script would look like, something like on page 101 here, where I have my model, the binomial Jeffrey's prior is a beta. Again, we're going to compare that against a goal of 0.01. So you're going to see a step function down here. And I'm actually doing a lot more calculations than I need to here. So for example, this line here where it says P dot not goal, that's the probability of not meeting my goal. I can kind of move things around. P dot goal dot check is the probability of meeting my goal. Again, flipping kind of between success and failure space almost in a sense. I'm calculating the probability of seeing 0 failures in 250 demands. Up here, I'm calculating probability of seeing 0 or more failures in 250 demands. But the key parts here are the step functions and where I'm doing the Bayesian analysis. And so when you run this script, what you will find out is the probability that you're meeting your goal, which is given by this last line here, ends up being 83%. Remember, we wanted to meet the goal with 95%. And so we're really, given this data, we're really not meeting our goal yet. Probability that we see 1 or more failures in the next 250 demands, 64% chance. And so let me go back to the figure. So what I saw here was instead of a 95% chance of meeting my goal, we only have an 83 right now. Currently, given what I know, given that I saw 1 failure in 250 demands, we're only 83%. So in other words, this red shaded curve is 83. The darker shaded curve is 17%. I'm close to meeting my goal, but I haven't met it. What it would take to meet my goal is I would have to have more demands and no failures. So I'd go out and test the fuel cell maybe another 50 times. And let's assume I go out and test another 50 times. I don't see any more failures. All I would do then, I would go back, rerun this. I would change n to 300, x equal 1, and then this would go up to, I don't know, it might be 0.95, it might be 0.92, it might be it'll go up. I don't know how far it'll go up with those 50 extra demands, but I can calculate that very easily. And in fact, you could then use this script here to say, how many more demands do I need to see without a failure in order to reach 95% confidence? And it might be 50, it might be 60, it might be another 100, I don't know, but you can calculate that. Okay, and then this slide just dumps out all of the gory detail. And again, the 83% comes from those a couple of those lines that I monitored. The probability that I fell in demand is on average 0.0069, and then the 5th and 95th percentiles. Okay, and then the last topic we have today is just a different kind of a model. There's a model called GEV, or Generalized Extreme Value Models. It's frequently used to represent kind of the worst events, so extreme events. And so we use this model a lot for climate kinds of things, flooding, sometimes earthquake modeling, but sort of really bad events, outlier events, 1 out of 100 or 1,000 or 10,000 year kinds of events, and so on. The details of this is in chapter 13 of the book, but we'll look at, a case here. And this is just a hypothetical model where this model represents, let's say, a flood or a heavy rainfall, where the magnitude of the event in meters is given by this simple equation, 0.5 plus 0.5 times the logarithm I, where I is the return interval. So the longer I wait, the worse the events I could see. Just a very simple model here. And what we're going to do is use this model to make some sort of synthetic data, and then compare that to what a Bayesian analysis would give us. So I take that model, I calculate for different return intervals, different magnitudes. So in other words, this little data table comes from this example, and this is just something I made up to produce data. I could go out, for example, NOAA has weather-related, this would be rainfall data, where in this case, if I look at a 1-day window, so in 24 hours, every 1,000 years, I would expect to see a rainfall event of 9.39 inches. And I don't remember where I took this data from. It's a specific, I think it was on the East Coast someplace, but NOAA has data tables that show us return interval, magnitude, and so I just made up a model. So I'm going to use this first data table. I'm going to go into OpenBugs. I'm going to then use the generalized extreme value model to see, can it make predictions similar to what the model is telling me. And I'm going to, if I look at my data, I went up to a 1,000-year event. But what I want to do is, can I predict 2,000 and 10,000 year events out of OpenBugs? The answer, of course, is yes. Just like we saw predictions earlier today. The only thing that's new here really is I'm going to use an extreme value model. And to do that, I set up the infrastructure for that and loop through the data. So the data that I had was the magnitude events related to 1 year, 2 year, 5,000 or 5 year, clear up to 1,000-year events. I had the outcomes, the magnitude of those events, but you notice I did not have any data for 2,000-year events, nor did I have it for 10,000-year events. Those are not available. I don't know what those are. But OpenBugs is going to say, well, hey, we can estimate these based on the uncertainty and the fact that I have a GEV model. So I'll fill in the blanks here. To do that, though, I have to have the GEV model. Again, all of the blue text here is just setting up the GEV model explicitly. And so this is just the math to say, make a GEV model. The magnitude as a function of time. The rest of this is then setting up non-informative priors for the GEV model. And this is a little more complicated, mainly because the GEV model has 3 parameters. The models we've dealt with, like the exponential, had 1 parameter. The log normal and the gamma and the beta had 2 parameters. The GEV has actually 3 parameters. In this case, they're actually mu, psi, and sigma. But anyway, we have to have non-informative priors for the GEV model. So it's the same general approach, just using a general, the GEV rather than an exponential or some other easier model. Okay, so really nothing new here, just a little more complexity. I run that. I tell OpenBugs to run that script, and then it will give me then is the outputs in terms of uncertainties at each of the data points. So for example, at a 2,000-year event, I will find that, and I've just plotted these in Excel, I'll find that the mean value is a 2.2 meter event. So in other words, in Excel, I just went to 2,000, plotted 2.2. 10,000-year event, what OpenBugs tells me I should expect to see a 2.6 meter event, which is that point up there. And then also there's uncertainty, and I plotted the 90% interval for each of these. And those are simply data tables that would come out of OpenBugs. I've just translated those into this nice looking curve in Excel. Okay, so I had, again, a hypothetical model, gave me some data points. I ran that through a GEV model, making prediction on 2,000, 10,000-year events. And then the exact answer, the blue curve, is very similar to what OpenBugs calculated. So this model worked pretty well for the example that I was looking at, which is nice. Okay, so again, we're almost out of time, but 4 hours to cover a whole book is asking a lot, but we actually covered a lot of subjects. Uncertainty in data, many different kinds of PRA models. There's a lot we did not touch on. Bayesian model checking, hierarchical, where you can have models kind of nested within models, Bayesian regression, how you can have fault tree models completely Bayesian informed. So there's more to do, of course, but we're out of time for today. So go out, get the software, definitely. Buy the book and use it. If you have questions, let me know. The plan is we will put the slides and the actual video up on the PSAM websites for links. And so this will be a historical record of the event, but you'll be able to refer back to both the slides and the video once